Additive manufacture is the industrial production name for 3D printing, a computer-controlled process that creates three-dimensional objects by depositing material, usually in layers. AM technologies can broadly be divided into three types. The first of which is sintering, whereby the material is heated without being liquefied to create complex high-resolution objects. Direct metal laser sintering uses metal powder, whereas selective laser sintering uses a layer on thermoplastic powders so that the particles stick together. The second AM technology fully melts the material. This includes direct metal laser sintering, which uses a laser to melt layers of metal powder, and electron beam melting, which uses electron beams to melt the powders. The third broad type of technology is stereolithography, which uses a process called photopolymerization, whereby an ultraviolet laser is fired into a vat of photopolymer resin to create torque-resistant ceramic parts which are able to endure extreme temperatures. Additive manufacture allows for complex models to be created, which previously would have been impossible to fabricate due to traditional manufacturing limitations. The following case study aims to demonstrate how a basic manifold block can be greatly optimized by additive manufacturing processes. Subtractive manufacture only allows for straight bores to be drilled. If the direction of flow is to be changed, an intersecting bore must be drilled and then capped off, as can be seen here. This in turn causes excessive turbulent flow, which reduces overall hydraulic performance of the manifold, and in worst case scenario results in cavitation, resulting in reduced life cycle of the component. Extensive advancements into additive manufacturing technology has been made in recent years. Additive manufacturing allows designs with complex geometries to be created which would have previously been impossible to achieve. To demonstrate the potential benefits additive manufacturing could have in hydraulic applications, a case study has been carried out on a basic manifold block. The original block has sharp bends, as can be seen here, and redundant pilot bores, which can be seen here, which result in turbulent flow and reduced overall performance. Additive manufacturing allows the block to be redesigned with optimum fluid flow in mind, allowing the internal channels to be greatly enhanced. Redundant bores can be removed, resulting in removal of unnecessary fluid travel. The channels can also be smoothed out to reduce turbulent flow and improve overall hydraulic performance. Subtractive manufacturing techniques result in an abundance of excess material, which is surplus to the requirements. Additive manufacturing allows a topological optimization study to be carried out on the component in hand to understand the areas of material which can be removed, while still allowing the manifold to meet all required constraints. Areas such as this here can be removed to optimize the design. A topological optimization study was carried out on the concept manifold. All constraints in which the manifold must meet during operation were inputted prior to running the simulation. The study achieved a 64% reduction in component weight, an 87% reduction in the volume of material required to produce a component. This in turn greatly reduces material costs. The optimized design met all operational constraints. Please refer to the following slide for confirmation of these constraints. Prior to running the topology study, the loading conditions were applied to the model to ensure the optimized design meets required constraints. The manifold is to operate at 300 psi during normal working conditions. A fixed geometry was placed on the mounting bores. All internal fluid channels were subjected to a 500 psi pressurized force, ensuring that a 1.5 factor of safety is achieved in the optimized design. When simulated, the topologically optimized design met all operational constraints. No excessive stress or areas of extreme concern were noted. The blue shows an area of little to no stress. The green areas show areas that are slightly more stressed but not of concern. The yellow and red areas have high stress but are still well within the design constraints. No excessive deformation was noted at this time. In order to understand the potential benefits of the optimized design, a CFD simulation was carried out on the below simplified models. As can be seen in the image to the left, the original design causes turbulent flow at the sharp change in direction. As a result of the poor fluid path, high pressure losses are experienced within this design. The cumulative effect of these pressure losses in turn results in large pumps being required to maintain required pressures. This results in inefficiencies in operational practice. Further to this, the turbulent flow creates excessive noise and vibration, which can reduce the life cycle of equipment and promote leaks, as well as causing an unpleasant working environment. By adopting the curved channel, which can be produced by additive manufacturing, the flow path is much smoother. This results in a reduction of pressure losses of 48% in this case, and the elimination of turbulent flow. It has now been confirmed that the overall efficiency of the hydraulic system has the potential to be greatly improved by adopting the additive manufacturing method. Less noise and vibration will occur, resulting in improved component life cycle and a more pleasant working environment. A primary concern when manufacturing the manifold by means of 3D printing is the amount of complex support structures that would be required to support the channels during manufacture. It would be hard or even impossible to remove all support structures after printing. Therefore, research was conducted on how to best resolve this issue. A slicing software was found which allows particular support structures to be reduced in size or even removed from the design as required. The support structures were reviewed and several internal support structures altered, particularly within bends in the channels, as these would be hard to remove during the post-processing phase. A prototype was then printed to ensure the support structure removal was possible. As can be seen in the image, this was successful. The prototype was printed in the horizontal build position. This position was selected as it would provide the quickest and cheapest print. It was noted that it was difficult to remove the internal support structures in the long channels even after utilizing the slicing software. Please refer to the arrow on screen now. On reflection, it is advised that the position shown in the image to the left is utilized for printing. This would remove the need for support structures within the long channels, as no print angle within them would be over the 45-degree limit. The prototype was 3D printed utilizing the fused deposition modeling process. A PLA feedstock material was used to make the prototype. PLA is one of the most popular material selections for 3D printing due to its ease of use and minimal warping issues. PLA is one of the most environmentally friendly 3D printing materials, and unlike alternatives such as ABS, is biodegradable. PLA provides a low-cost printing option. However, this is best suited for non-functional prototyping purposes or low-stress applications due to its brittleness. All calculations and simulations have been based on the optimized model being printed in aluminium. Aluminium is a lightweight alloy with good strength, high flexibility, and outstanding thermal properties, which are highly desirable in hydraulic applications. The properties exhibited by aluminium makes it the perfect material for the manifold application. Further to this, oil field equipment is exposed to corrosive atmospheres. Aluminium exhibits high corrosion resistance, which is critical in this application to prevent premature failures. If the optimized design was to be printed for industrial use, the best printing method would be selective laser sintering. SLS makes use of powdered metal feedstocks to build the model. An energy source is then directed at the feedstock by a CNC to fuse the atomized metal powder together to create layers of the model. The process works in the following way. A thin covering of metal powder is laid on the build platform of the aluminium 3D printer. A laser selectively binds parts of the powder to build a solid layer of the model. The build platform lowers, and the printer uses its recoater to distribute another covering of metallic powder on top of the previous layer's fused and unfused powder. At this point, the process repeats itself layer by layer until a complete model forms. It is crucial to note that the melted powder is cooled quickly to form the metal. By utilizing SLS, the concern with the support structures is removed. This is due to the unfused feedstock material acting as support structures. This will guarantee the channels of the manifold are free of any foreign matter. When utilizing the SLS printing technique, the final product will be buried in the printing powder. It is economical to spend time removing this powder and then filtering for reuse to save on future material costs. The rapid heating and cooling the material is subjected to during the SLS printing process leads to internal stresses being induced on the component. The part must be left on the build plate and then placed in an oven or similar to relieve the stresses. In practice, a manifold will have threads to hold various fittings and valves. The threads should be cut during the post-processing phase. To improve on surface finish, the manifold should have the external features subjected to a light sandblast to reduce the appearance of layers. Internal bores should be lightly polished to improve surface finish. The manifold should then be anodized to further enhance the cosmetic appeal and to further increase the corrosion resistance. The key takeaways of the case study are as follows. The volume of the material required to produce the component is greatly reduced. As a result, the component weight is significantly reduced, in turn allowing easier handling. Further, the cutouts allow for greater clearance during installation. The fluid flow is greatly enhanced with the elimination of turbulent flow, which in turn reduces pressure losses. The overall efficiency of the manifold is greatly improved. The offshore drilling sector is becoming fiercely competitive due to volatile oil prices. Operators have a key focus on ensuring drilling activities are as efficient as possible to ensure maximum output in a given time frame. Any delay in hydraulic operation could lead to increased timeframes. The cumulative effect on inefficiencies in hydraulic manifolds across the drilling package could lead to significant delays in routine operations. It is suggested that a poorly performing manifold, such as the BX elevator manifold, is identified and studies carried out on inefficiencies. The manifold design should then be optimized, such as the case study, and improvements in efficiency documented. I would like to take the time to thank you for watching this presentation and would welcome any questions or feedback on the case study.